Okay, so I suppose I'll get started. So I welcome the viewers to this problem solving and live interaction session for the subject engineering mechanics. Today we will be dealing with the topics from week 4, which is essentially to do with beams. Okay, so let us take a look at the first problem. So we have been asked what is the magnitude of the vertical reaction offered by support A in kilonewton for the given loading. So we can see that we have been given a simply supported beam which has a pin here and a roller here. It has been applied with a concentrated load of 1.5 kilonewton at this point, which is at a distance of 1 meter from A, and it is applied with a clockwise couple of 3 kilonewton meter at a distance of 5, 5 meters from that support. So in the last session, we discussed how supports work. Essentially, for a pin support, we have two unknown reactions, namely, if the support is A, we will denote it by AX and AY, essentially in the horizontal and vertical directions. And for the roller support, we know that it offers only one restraint, which is in the vertical direction. So with that background, let us try to solve this problem. We essentially have to find out the magnitude of the vertical reaction offered by support A. So for that, first we need to draw the free body diagram. So let us go ahead and draw the free body diagram. Let us say this is the beam. These are the two pins. I have a vertical force, call it AY, call it AY. Then I have a horizontal reaction, call it AX. At this end, I'll be having a vertical force. Since that is labeled as B, I'll label it as BY. And at this point, I have been given that the concentrated load of 1.5 kilonewtons is applied. And at some other point, I have a clockwise couple of 3 kilonewton meter. So let me just add a page here. Okay, so this is my free body diagram. I'll shift that free body diagram here. Uh, yeah, Mr. Nishant, could you? Yeah, thank you. So now what we need to do is we know that this beam is in equilibrium and we have the XY plane. We have the beam in the XY plane. We have been given the direction of X and Y. Say this is X and this is Y. So we have the free body diagram of the beam, which is complete. Now I can apply the equilibrium equations. What are those? In the XY plane, I have essentially three equilibrium equations, sigma fx equaling 0, sigma fy equaling 0, and sigma m about the z-axis equaling 0, but mostly we will be dropping that subscript and denoting it with some alphabet which indicates the point about which we are taking. So to that end, I hope that is clear. So I have this point as A, B, and I have C and D marked here. So this is C, this is D. Now my question wants me to find out what is the magnitude of the vertical reaction offered. That is all that is asked. I could go about systematically solving each and everything and then coming to the value. Instead, what I can do is it has asked me the vertical reaction. So this has no bearing on the horizontal reaction because both are independent. So essentially, I will apply sigma Fy equal to 0 first. So what does this give me? Ay, since it is pointed in the positive y direction, so that will be positive, minus 1.5 kilonewton. And mind you, we are adding up the forces. So this is not a force, this is a couple. So it will not appear in our force equilibrium equation. What else is there? We have By. No other vertical forces are there. So this equals 0. And this gives me Ay plus By adds up to 1.5 kilonewton. This is one of the equations that I have got so far. Okay. Now I know that sigma fx equaling 0 would trivially get solved because there are no other horizontal forces, so ax is equal to 0. So we have already used up two equilibrium equations. So we need to use the third one to find out what ay is. Now, is it possible for me to find out ay? uh, I can take the moment about any point. Essentially, this beam is in equilibrium. So moment equaling 0, some of the external moment equaling 0 should be holding at every point in space. But my idea is to solve for ay quickly. So if I take moment about this point B, then the contribution of by essentially becomes 0. So at once I can essentially solve for ay, which is what I should have started with. Even the sigma fy equaling 0 is not required in that case. So let us go ahead and do that. So I'll take sigma moment about point B. This is to be clearly understood that this is moment about the z axis at the point B. So this is moment at point B equals 0, which gives me, I can see that force is pointing this word. So this will create a clockwise moment at B. So its contribution will essentially be negative. So minus ay into what is the length of the beam which is given. This is 1, 4 and 1 is what is given. So the length of the beam is 6 meters. Plus, I know this force will create a anti-clockwise moment there. So it will be 1.5 into 5 since I have subtracted out that distance. Now we should definitely account for this couple since we are adding up the moments. So I can see that this is a clockwise couple, which implies that it is negative and plus by into 0 since it is applied at that very point. I may as well not write it, but I'm writing it here for clarity. So I can essentially remove this quantity and write that this is equal to 0. Now I can solve for this. So this gives me 6ay equals 1.5 into 5 minus 3, or ay is 1.5 into 5 minus 3 divided by 6. So what does ay come out to be? It is 0.75 kilonewton. So ay comes out to be 0.75 kilonewton, small k. And we have been asked the question to solve for ay only. So we can see that our answer is 0.75. If we were to solve for by also, we can use this equation. We can use equation number 1 and solve for it, which is nothing but dy equals 1.5 minus 0.75, which is again 0.75. So both the reactions are equal, but this is not due to symmetry of the problem. Essentially, there will be cases when I have a beam like that, and then I have a central load of maybe 1.5 Newton, 1.5 kilonewton that gets distributed evenly. This is not because of symmetry. This is because the effect of this and the effect of this moment is making the system symmetrical, but it is not otherwise individually symmetrical. So I hope that this is clear. If there are any questions, you please feel free to go ahead and ask midway. Otherwise, I'll proceed. Is it clear, whatever we have seen so far? I hope that this is clear. Anyway, this reaction calculation we have been doing for some time. Now we'll get more into deep beams to see how to, arrive at other quantities. Namely, in the area of beams, we have two quantities which we will be dealing with. Essentially, one is a shear force, which we'll denote by V, V for victory, and we have a bending moment. which we should ideally denote by MB, but for the sake of brevity, we will call this as M. So, or M or M of X at some X distance, we will call it as M of X. So, okay, so there is something that we need to focus on here, which is the sign convention for beams. So we have been seeing till now that when we write a position vector A with respect to C, or when we write any vector, for example, A with respect to C, this implies that the origin is at C. So this is a convention. Similarly, if we look at truss members, if we look at trusses where let us say this is supported by a pin and a roller, and let us say that I have marked the forces like that. Under the action of some force, under the action of some force, let us say that I have marked the internal forces like that. So what is the convention here? We discussed briefly in detail actually in the last session that in order to place the forces on the same side of the pin, which is the member side of the pin, we will be following a convention that towards the pin, if this is the pin, if there is a member force pointing towards the pin, it will imply compression. And if we have it away from the pin, then this would imply the member is in tension. This is the convention we started with. And how do we go about solving problems in trusses? First is we assume all the members are in tension, which means when I start solving this truss, I will put all the forces to be pointing away from the joints. Once when I solve it, if my answer is correct, it implies that the assumed direction is correct. If my answer is negative, then that implies that the assumed direction is, it requires to be reversed. That is, I had started out with considering the member to be in tension, but a negative answer would imply that it is indeed in compression. So this we have seen. So such conventions are very much prevalent in engineering, and these need to be accounted for so that it is people are easily able to interpret the results. Similarly, for beams also we have one convention. So the beam sign convention will appear something like this. Positive shear force, and the direction will be given like that maybe. Similarly, positive bending moments, it will be given like that. So we need to look at what these mean. This will be given in most of the questions. So we need to interpret this appropriately. What this implies is that on the positive face, this is the positive face, this is the negative face. So on the positive face, we will indicate a force that is pointing downwards, and we will label that as positive shear force. We will label the positive shear force. If we are in a positive surface, we will point it downwards. If we are in the negative surface, we will put a force that is pointing upwards and say both these are positive shear forces. Similarly, when we go to bending moment, when we are at a positive surface, I'll subsequently explain what do you mean by surface, and this application will become more clear as we apply it to one of the problems. So if I have a positive surface, I will put a moment that is pointing in the that is essentially anti-clockwise, and I'll call this as a positive bending moment. Whereas if I am in a negative surface, I will put a clockwise moment and say that it is a positive bending moment. Similar to trusses, first we started with one convention that we have to apply forces pointing away from the joint and we will take them to be in tension. Similarly, for beams, we will no longer be dealing with joints, we will be dealing with surfaces. So for a positive surface, whenever I encounter a positive surface, I'll quickly follow the sign convention. I'll put a force pointing towards the bottom and I'll put a anti-clockwise moment. And I will consider that according to my sign convention, I have put a positive shear force and positive bending moment. Same thing, if I have a negative surface, I'll put a force pointing upward and I'll put a clockwise moment and say that I have considered my sign convention, I have put positive shear force and positive bending moment. I hope that is clear. Now, how to identify a positive surface is the question one might ask. So let us look at that in a little more detail. Let us say that I have a okay. Let us say that I have a beam like that. Let this be connected. So let us say this is my beam in 3 dimensions. Now what I'll do is I'll pass an imaginary section, a plane essentially. Let me put it like that. So this is just an imaginary section. I cut this beam with a section like that. What this section will do, it will virtually cut that beam into 2 segments. And those 2 segments, let us see what those are. So essentially I have cut this here. So I'll be having something like that. Let me just connect this and I'll have the another section which is essentially which will look something like that. So the section has been separated. The section has separated the beam into 2 components. And if I were to draw this with the 2 components, we can see it will essentially be a dotted line here. Okay, that is not visible. That will be on the other end. Now let us say that I have my coordinate system like that. Let us say this is X, this is Y. So I'll have Z pointing in that direction. Now every surface is characterized by its outward normal. So if this is my surface, if this is my surface that is exposed, this is characterized by its outward normal. Similarly, since that is not visible, I'll just draw it in dotted line. For this surface, my normal will be that. So for a surface whose outward normal coincides with the coordinates positive direction is called a positive surface. A surface for which its unit normal is opposite to the positive coordinate direction is essentially a negative surface. So with this background of understanding, I can label this as a positive surface and this as a negative surface. All this might it will become clear as we go on to a problem and solve it. Now I have drawn the beam in 3 dimensions, but for the sake essentially we will be dealing with planar beams. So we will be analyzing only one of the sections. So in that case, what will happen is we will be having two-dimensional representations of them. The same thing, I will represent it in two dimensions. So I will have the section like that. The section which I cut will be this, and I will be exposing two surfaces here. This I'll erase and this let me erase. So once I cut that section, I have exposed two surfaces for which the outward normal is like that, and for this surface the outward normal is like that. So it's the same thing. So this will be a positive surface. So this surface will be positive and this surface will be negative. Why? Because my positive coordinate direction is pointing in the same direction as my outward normal. Once I identify the positive surface, I just have to follow this convention. As we discussed, on a positive surface, I'll simply label shear force as something pointing downward according to this convention, and I'll say that I have put the positive shear force there. Similarly, on that positive surface, I'll put a moment that is anti-clockwise, and I'll say I have accounted for positive bending moment there. So this is all that needs to be done. So I hope that this is clear. With this background, let us go ahead and look at this question. Yeah, are there any questions about what we discussed? And is there any, if there is a need for me to explain this in Hindi, I can do that. Please let me know. I hope that this is clear what we have discussed so far. Okay, so I take it that it is clear. So I'll move on. Now we have been asked what is the magnitude? What is the magnitude of the maximum shear force in kilonewton experienced by the beam for the given loading? So essentially, first we need to find out shear force at each and every point in this beam. How we do that, how we go about doing that is we essentially map as a function of x shear force as a function of x we will plot, and we call that plot a shear force diagram. Similarly, bending moment as a function of x when we plot, we call that as a bending moment diagram. How these are useful? Once we plot for a beam, we plot a shear force diagram and bending moment diagram. At once I have a representation about how the variation is and what are the extrema, that is positive and negative bending moments or positive and negative shear forces. And when we design beams, we will essentially be considering only the maximum of those values and go about doing our design. Okay, so let me first draw the free body diagram for this. I have put the beam. I'll replace this by AY, and then I have a force like that, which I label as AX. I have one reaction, BY. Then I have a point load, which is 0.5 kilonewton. I have 3 kilonewton applied like that. And then I have another 0.5 kilonewton applied like that. So let me just take this and put it in a new page. So this is my beam. Now again the same drill that we did, sigma fx equaling 0 gives me ax equal to 0. One of the unknowns we have solved. Now sigma fy equaling 0. we can do the same way as we did for the first question and go about solving is, but one thing we can strikingly note that this is at a distance of 1 meter from the left support, this is at a distance of 1 meter from the right support. This is 2 meters, this is also 2 meters, and the loads are same. The beam is fully rectangular, there is no variation in the cross section. So essentially it's a symmetric loading. So AY and BY would come out to be the same from symmetry arguments. Now these two forces are keeping this entire beam in equilibrium, and if they are same, essentially the magnitude of each should be half of the sum total of the forces there. So what is the sum total of the forces there? 3 plus 1, which is 4. So essentially I will have 2 kilonewton applied here and 2 kilonewton applied there. From symmetry, I can see that AY equal to BY equal to 2 kilonewton. So far we have only calculated the reactions, but that is not what is asked. What is asked is what is the magnitude of the maximum shear force. So essentially we need to plot the shear force diagram. Now here I have been given the XY coordinate system. So what I'll do, I will set my origin here for this beam. So let me set my origin in at this point. Let me take this to be the X direction and this the Y direction. So if I were to take a section like that, if I take a cut section like that as we saw earlier, this cut section will be at a distance of, let me move this here. Let AY be here. So from this point, this is at a distance of X. And X can vary between 0 and total length L. I hope that is clear. So for each and every one of these points, I will have, these are essentially the key points where I need to find that. Why? Because if I consider the beam in this section AC, I have a load applied, there is nothing else changing. But as soon as I cross C, I have a force that is applied like that. As soon as I cross D, I have another force applied like that. And E and so on. So at each and every point where there is either a load, either a force or a couple applied, I have to break my section. We'll see why that is. Okay, so first let me draw the free body diagram. Let me say that I consider a section X such that 0 less than X less than 1. So this is essentially, if you see, it is portion AC. I'll just label them A, B, C, D and E. So for portion AC, this is my condition for X. So let me, essentially what I'm saying is, I'll take the cut here between A and C. So let me take that and draw the free body diagram. I have a force applied like that, which is 2 kilonewton, which is nothing but my AY, which is applied here. I don't have any horizontal forces here. And since I am still in between A and C, this force will not appear in my free body diagram. What else should appear? I should identify that this is a positive surface because it has a outward normal like that, which is coinciding with my positive X. So it's a positive surface. Now let me revisit my question. My question shows that this is my sign convention to be used. So let me take a copy of that sign convention. This is my convention with the understanding that these two denote the positive surfaces and these two denote the negative surfaces. So this is a positive surface. On a positive surface, I note that I have to put my shear force pointing in the downward direction. So I simply do this. I put a shear force there, label it Vy. Now my free body diagram is complete. Or rather, I should also put, once I have put the shear force, I should also put the bending moment. This is a positive surface, so I'll put that as M. Or rather, I should put it as Mx because this distance is x. I hope this is clear. So for portion AC, I have drawn the free body diagram, and according to my sign convention, I have put positive shear force and positive bending moment on my free body diagram. Once I have done this, if my answer comes out to be positive, it is in this direction. If my answer comes out to be negative, the direction needs to be reversed. That is all. Same drill, whatever we have done for trusses, the same drill we are doing here. That is all. Only except for one quantity, there are two quantities here, namely shear force and bending moment. Now I apply my equilibrium. Now this whole beam is a rigid body for the purpose of this course. Now, if a rigid body is in equilibrium, then any subsystem of that should be in equilibrium, which implies that this subsystem which I have taken for the beam, it must be in equilibrium. Now, how do my main motive is to solve for these two in terms of the load applied. Now, how do I solve for Vy? I simply apply the condition sigma Fy equals 0. What does that give me? Plus 2 because it is pointing in the top upward direction. And then I have minus Vy equaling 0. Since I am adding the forces, my moment will not appear in that equation. So what does this give me? Vy equals 2 kilonewton. Does this imply that Vy is 2 kilonewton throughout the beam? This implies that Vy is 2 kilonewton as long as this range is not violated. So essentially I have solved for the shear force in section AC where x is 0 to 1. I hope this is clear. Similarly, let us do one more section and then we'll quickly draw so that it becomes clear. I'll just copy this. Now let me take x to be varying from 0 to I want it in this section. Sorry, I want it in this section. So my x has to vary from 0 to x has to vary from this point to this point, right? X is varying from 1 to 2. X equal to 1 is my starting point. X equal to 2 is my ending point. 1 less than x less than 2. This is portion CD. Now my diagram would still be the same essentially. Only difference is I have a longer section. Sorry, 1 minute. I have a point load, a concentrated load that is applied at 1, whose value is 0.5. And this x again is like that. Now once I understand that this is a positive surface, I'll label the, according to my sign convention, I'll put a downward force and call it positive shear force, and then I'll bring in a anti-clockwise moment and call it positive bending moment. Now again we have to do the same drill. Let me just draw this a little more clearly. So now if I take sigma y equal to sigma fy equaling 0, what do I get? I get 2 minus 0.5 minus Vy equaling 0, which gives me Vy equals 1.5 kilonewton. And this is valid for this section. Vy is 1.5 kilonewton. And for this section it was 2 kilonewton. So you can see as I vary x, as I go from portion to portion, I am able to see that it is reducing. It was 2 initially, then it was 1.5. Now we can easily see, once I have my section over here, initially I had 2, then 0.5 got subtracted for this portion CD. Now I can see that for DE, 0.5 and 3 will get subtracted. We can draw that same free body and start doing it, but the idea is once we understand it, we should try to pick up some speed. So by inference, I won't solve it, but I'll say by inference, what can I write? For 2 less than x less than 3, which is portion DE. My shear force should be 1.5 minus 3. It will be minus 1.5 kilonewton. Similarly, for 3 to 4, what is this portion? This is EB, the last portion. Now we can see all the forces will get subtracted. So 2 minus 0.5 minus 3 minus 0.5. So it will be minus 2. Minus 2 kilonewton. Let me write it again. So for my beam, at each and every section that is divided by the load, namely AC, CD, DE, EB, I have the shear force variation now. Essentially, it is constant in those section. In the initial section, it is 2, then it comes to 1.5, then it goes to minus 1.5, goes to minus 2. In that case, if I take this to be my beam, and I have 0.5 kilonewton applied there, I have 3 kilonewton applied there, I have the reaction 2 kilonewton. So if this is my beam, I have essentially solved for all the sections. I have solved for all the sections. So now let me just map it out in the form of a diagram, which is otherwise known as the shear force diagram. It might look a little tedious, but once we get the fundamentals clear, we can start going about at a higher pace. So I hope you can bear with me there. Okay, now I have my sign convention here. Let me get my sign convention there. So as of now I'm looking at only shear force. So let me not worry about the moment as of now. So I draw the datum, which implies V is equal to 0. Now for the first section, I saw that according to my sign convention, V is 2 kilonewton, and that varies from 0 to 1, right? So from 0 to 1, I have it goes up like that and becomes this is 2 kilonewton. Then at 1, it had an abrupt change, and for this portion, it was 1.5. So if this is 2, then this will be 1.5. Then at this portion, it had an other jump and became minus 1.5. Throughout this portion, it was minus 1.5. Then finally, it became minus 2 and it connected back to 0, implying this is positive, this is negative. This quantity is 2 kilonewton. This quantity, this is 1.5 kilonewton. This is minus 1.5 kilonewton. This is minus 2 kilonewton. So this is the procedure to draw the shear force diagram. I know that for some of you who are familiar with this, it might be a very circuitous way to do it. You can quickly write the shear force diagram. But for the interest of getting the fundamentals clear as to why we do this, I thought it will be better if I go section by section. So to that end, I hope I made it clear. So we can hatch this with some color, and this will be our shear force diagram. And shear force diagram is always to be reported with its corresponding sign convention. Otherwise, it doesn't essentially convey the meaning properly. Okay, now that we have the shear force diagram with us, let us revisit what the question is asking. The question asked us to report the magnitude of the maximum shear force. Now from our shear force diagram, we can see that the maximum shear force that is being transmitted by the beam is, here it is 2 kilonewton, here it is minus 2 kilonewton. Is there any necessity that this and this should be the same? Absolutely not. Most of the times it will not be the same. It is because of our symmetrical loading. We saw that our reactions were equal, which is why these two are coming out to be the same. In case if it is not the same, according to our question, we have been asked what is the magnitude of the maximum shear force. So the maximum shear force, if let us say this was 3 minus 3, then this would have been our maximum shear force. And we need to report the magnitude of that, which is essentially, which would have been 3. In this case, our maximum shear force is 2 and minus 2 are one and the same. So essentially, we have the maximum shear force as 2 kilonewton because we have been asked for the magnitude. So with this question, I suppose we are somewhat confident about drawing shear force diagram. We will be dealing these, we have dealt with only point concentrated loads. We will be seeing in the subsequent examples how to go about solving for uniformly distributed load, uniformly varying load, or any cubic curve, sine curve, whatever be the case, we'll be easily able to solve for it. So if there are any questions in what we discussed, you please go ahead and ask. Everything is clear? कुछ समझ में आ रहा है? मैं मतलब if you want me to explain it in Hindi, I can. तो आप जिनको जरूरत है आप बता दीजिएगा अगर कुछ समझ में नहीं आ रहा है तो. Okay, I take it that this is clear. ठीक है, then I'll move on. Now we have seen how to draw the shear force diagram. The same thing what we do, see we have essentially taken this for this section, we took For this portion 0 to 1, we draw the free we drew the free body diagram. We labeled Vy and Mx according to our sign convention given here. Once we did that, we solved only sigma Fy equal to 0 and got the shear force. Now, in a similar vein, if I do sigma M equal to 0, I will be able to get the bending moment variation. And if I go about plotting it in a similar way as I did for shear force diagram, I will have the bending moment diagram. That is all there is. But so at times, our bending moment will have some dependence on x, maybe linear, quadratic, or cubic, or whatever. In such cases, it is important for us to know because you can draw parabola in two ways. So we should be able to gauge which one is the correct way to go about. So we should essentially relate our moments, our shear forces to the applied force and go about solving the problems. So let us try to do that. Essentially, it has been done in the lecture, so I'll just recap it a little quickly. So if we see the interrelationship between the load, the shear force, which is denoted by V, and the bending moment denoted by M, let us say that this is my sign convention that I've been given. There is no dearth of sign convention. It is not sacrosanct. It is quite possible that you might come across examples in books which use a different sign convention. So the idea is not to stick to one convention. The idea is to interpret and be able to solve questions once you are given a sign convention. So we will proceed with this sign convention that is given to us. And as we saw that beam, the long beam, I have just taken a portion of that beam here. I have taken a portion and let my positive coordinate direction be like that. So essentially I have this as the positive surface and I have this as the negative surface. So on the positive surface, I label forces that are pointing downward and say that this is a positive shear force. Similarly, I'll put moments that are anti-clockwise and say that those are positive bending moments. Same opposite of that I'll do in the negative surface. And I have applied a load that is pointing downward. Let us say the distributed load is W, applied through a length delta x. Now, since the beam is in equilibrium, this subsystem has to be in equilibrium. If I solve for the force equilibrium, I'll be able to see, so this V is pointing upward. In force equilibrium, M will not appear. So I have plus V minus W into delta x. The unit of this W is Newton per meter, let us say. So I will get the force only when I multiply this with a distance. So this is essentially called a load intensity. I'll discuss about that more as I go about solving. And then I have minus V minus delta V. Why this delta V? Because as I go along, we saw that from one section to the other. In the previous example, in this section we had some shear force, then it abruptly changed. Now it abruptly changed because I have a concentrated load here. Instead, if I had a distributed load, it will gradually change without a sharp jump. So that change is being captured in delta V and delta M. So once I have that in equilibrium and I solve it and I take the limit where I take this to be an infinitesimal length, in such a case, I get a relation dV by dx is minus W. What this implies is the slope of my shear force diagram is nothing but minus W. And this is applicable for cases where I have distributed loads. Similarly, I can solve for moments also. If I take the moment equilibrium, M, at let us say I take it at this section, on the right section, on the, let me just write it. Equaling 0, it will give me minus M minus V delta x plus W delta x squared by 2 because this multiplied by this distance will give me a resultant force that is acting at the center, and that force will create a moment with a lever arm which is delta x by 2. That is why it is delta x by 2. This will not appear in my equation. M plus delta m will be plus, equaling 0. Now I can, by similar steps, I can solve this, and I'll get in the limit when delta x approaches 0, I'll get dm by dx equaling v. What does this tell us? It tells us the slope of the bending moment diagram related to the shear force value. And the earlier expression gave us the shear force, the slope of the shear force diagram with respect to the applied load. So these two relations are unique for this sign convention with which we started with. We are not supposed to overlook that fact that we started out with a sign convention here. We placed these positive shear forces and positive bending moments according to that sign convention and solved for its equilibrium and got these relation. So these necessarily have to be read in conjunction with that sign convention, which in other words implies that these only hold for this sign convention. So I hope that that is clear. If there are any questions, you please feel free to ask midway. Otherwise, I'll proceed. Okay, so I have these two relations. So let us look at the next question. Which of the following is or true with regard to beam analysis? Shear force changes at a section where a couple is applied. Now we saw that when I take a beam, essentially, okay, why don't I apply a couple? And let us say I have the reaction, let me call this point A. So I have AY, and I have applied some moment, some couple M. And this is at a section X, which is midway in the beam. So if I have my positive coordinate direction like that, calling this X and Y, then this is a positive surface. With my sign convention, I'll write Vy like that and Mx like that. So my free body diagram is complete. Now in order to solve for Vy, essentially I have to do only force balance. In force balance, M will never appear. It will only appear in moment balance. What this tells us is that shear force diagram is independent of any couples that are applied. So this is not true. Next statement says bending moment is maximum at a section where shear force changes sign. So let us say I have a function. Let us say this is my function, the graph of the function. Where will I say it is? It has an extrema. I'll say this point to be extreme. I'll say this point is the minimum. And why is that? Because I have a slope here. I have a slope that goes to 0, and then I have another slope following that. I'm able to see that. Let me draw it in different color. I'm able to see the blue slope is negative. Then I come to the red slope, which is 0. Then I move on to the green slope, which is positive. So at a point, simple from mathematics, we know that at a point where the slope changes its sign, we have an extrema. So we saw in the previous relation that the slope of the bending moment diagram is nothing but shear force. So when will the bending moment be maximum? When its slope will change sign. So yes, this is correct. Both bending moment and shear force can be maximum at a same section depending on the load applied. Any answers to this? Is it possible to have both bending moment and shear force that is maximum? Yeah, right. So if we have, let us say, for example, if we have a cantilever beam, so it is supported at the ends, applied to some load, general loading, and it is supported at the ends, maybe like that. So if it is embedded like that, essentially we'll be able to see that shear force and bending moment both will be maximum at the fixed end, at the clamped end. So this is possible. Yes. Last one is a section can of the beam can experience only bending moment without any shear force, depending on the loading and support conditions applied. So essentially we are talking about a condition which deals with pure bending. Pure bending meaning there is no variation of shear. What this question is asking is a section where bending moment exists but shear force does not exist without any shear force, meaning V has to be 0. This means that dm by dx has to be 0. So we are looking at cases where the slope of the bending moment diagram will be 0, or in essence where bending moment is constant. So if we take a case of a 4-point bend specimen, for example, if I take a beam like that, and then let us say I support it like that, and then I have two symmetrical concentrated loads applied. In such a case, for this portion, I will see that my bending moment will be constant, and essentially my shear force will be 0. It is also called a shear span, and all our beam formulations apply only to this region. So yes, it is possible to have, depending on the load and the support condition, it is very much possible to have a section which experiences only bending moment, also called as pure bending. So I take it that this is clear. So if there are any questions, please go ahead and ask. Otherwise, I'll move on to the next question. Okay, so this problem says, consider the cantilever beam loaded as shown, along with the sign convention to be used. Now we have been given a distributed force here. Before that, I just want to brief about distributed forces. I'll just add a small brief so that it becomes clear. Let us say again that I have a beam like that. Okay, and I have held it, and this entire area, the top area, is subjected to some pressure. So this is subjected to a compressive pressure of P. Now I know that pressure has units of MPa, or rather, let me make it simple, which has units of Newton per mm squared. Now in our beam analysis, we will be only looking at one section, meaning that will be the section that is passing through the center of this, center point of this. In which case, we will be considering the equivalent load that has been applied here. So if I just took the midsection of that, let me delete this. Taking the midsection, if I draw this as a midsection of that beam, from the side, I'll be able to see that this is applied with a pressure like that. But what will this load be? If I have to simulate the entire beam with this plane, then I should essentially nullify this dimension out. So if I multiply this pressure with this dimension, I'll be able to see that I will get a pressure intensity P1, which will be Newton per mm. So this is called a pressure intensity. This is a pressure intensity. Now, since this is uniformly distributed, since it was a pressure, it is uniformly distributed, I have this as a essentially as a rectangle. In such a case, at some distance x, if I want to find out what is the force. Oh, I see my screen is not getting updated. 1 minute. Yeah, I'm sorry about that. There's some issue with the internet. Okay. At this section, x, if I want to calculate the load, it will be nothing but the area of this, which is, what is the length? Length is x into P1. And what will be the unit? Newton per mm into mm, which will give me the force in newtons. So what this tells us is, once I have the pressure intensity diagram, the area of the pressure intensity diagram essentially gives me my total force. If this force is applied in a triangular manner, if this is applied in a triangular manner, I essentially have to take the area of that triangle. If it is applied at a sine curve, I have to integrate in order to get the total force that is applied. So that is all there is to it. I hope that that is clear. With that background, let us analyze this problem. So I have a beam and then I have a load applied like that. This load is 3.6 kilonewton per meter. This is point C, point A, point B. Okay. So at A, I know that it's a fixed end. So I'll replace this with two forces, AY, AX. In addition to that, there will be a moment which will support it. Because it's a fixed end, it doesn't allow rotation also. So let us call this MA. And I have the force like this. So anyway, let us first look at what is that is asked that in question. Which of the following qualitatively represents the shear force diagram for the beam as per the given sign convention? We have been given this sign convention and we have been asked which of these following is the shear force diagram for it and which of the following is the bending moment diagram for it. So we need to do that same drill. So let us look at that. Okay, I have it like this. So equilibrium tells me that AX is 0, AY is nothing but the area of this because it's a distributed load. And what is this distance? Both are 7.5 meter each. So this is nothing but, not half, sorry. It is 7.5 into 3.6. So AY is 27. 27 kilonewton. So we have used up two equations and we got two unknowns, AX and AY. Now for the moment, let us take moment about some point, let us say A. Adding up moments about A. Now it is essential to understand that if I have this load distribution like this, if I have a load distribution like this is similar to having an applied load like that. Because the resultant, because it's a uniform rectangle, it will have the resultant equaling 27 kilonewton. This is 7.5 meters. Both are statically equivalent. I hope that is clear. Otherwise, what we can do is we can take a section at some x. At some x, we can take a section and then integrate it from 0 to 7.5. So integrating a rectangle is same as calculating its area. So we'll be able to see that we'll get the same result here. Okay. Now, if I add up the moments, it will give me AX and AY don't have any contribution. I see MA is applied in the anti-clockwise direction because that is how I have applied it, considering it to be positive. So MA is positive, MA. And then this 3.6 is applied like that. This will create a clockwise couple there. Minus 3.6 into 7.5 is my load intensity. That load, not load intensity, it is the actual load. That load is applied at the center of this triangle. The center of this triangle is at a distance of 7.5 plus 7.5 by 2. which is 7.5 plus 7.5 by 2 equals 0. This is my equilibrium equation. So the moment, if I see, Ma is given as 303.75 kilonewton meter. I hope the calculations are fine. 3.6, yeah, 303.75. So we have got the reactions. Now we just have to take one section, the same drill. We'll take a section at a distance x. At a distance x, we'll take a section. We'll be required to take two sections here. One is varying from 0 to 7.5, the second one varying from 7.5 to 15. So let us do that. For 0 x to 7.5. That is portion AC. If I draw my free body diagram there, I can see that I have a force of 27 kilonewton applied, and I have an anti-clockwise moment of Ma. Let me call that Ma, with the understanding that Ma is 303.75. Any other load that I have to account for, this distance is x, with the understanding that x varies from 0 to 7.5. I know this is a positive surface, and I have the sign convention given here. I know this is a positive surface because this is given. So when I take a section like that, I have the positive normal in that direction. So this is my sign convention. Let me put that sign convention here, and I'll put Vy like that and Mx like that. Once I have done that, it is the same drill. Fy equals 0 gives me Py is 27 kilonewton. Vy I have got 27 kilonewton. Now let me take moment about some point, any point. Let me take the moment about this end to be 0. This gives me plus Ma, because Ma is in the anti-clockwise direction, minus 27 into x. This is my distance at x. So this will create a clockwise moment there, which will be 27x. Vy will not have any contribution. Mx is in the positive x direction. Positive, it is in the anti-clockwise direction. So it will have a positive contribution equals 0. Or this gives me Mx. The equation for Mx is 27x minus Ma. So as opposed to shear force, which was a constant value, I have got a variation in x, which happens to be linear because x is to the power 1. So at x equal to, now once I have got the equation, I can simply plug it, because this equation is valid for this range. This equation is valid for this range. So if I plug the extreme values, I'll be able to see what the values are. So at x equal to 0, so I'll have the bending moment at A. I can see that it is minus Ma. which is equal to minus 303.75. It is what we got. Kilonewton meter. At x equal to 7.5, I'll have moment at C, the middle point, which will be 27 into 7.5 minus 303.75, which is minus 101.25. So I have got the bending moment at these 2 points. Now I just need to do it for one more section. So let me go ahead and do that. Now for 7.5 up to 15, that is portion CB, the second half, which is the loaded half. There, if I draw the free body diagram, I have the beam like that. I have, this is 27 kilonewton, and I have this distance as x. Let us say this distance is 7.5. So after this, I have the load that is applied here. This load is applied, and this load intensity is 3.6 kilonewton per meter. I have a MA applied here, and this is point C, this is point A. Anything else I have missed? I have accounted for all the forces, but I have not accounted for the shear force and bending moment. Let me copy this, put it here. Again, this is a positive surface, so I'll have Vy applied like that and Mx applied like that. And I'll say I have followed the sign convention. I have applied my positive shear force and positive bending moment there. Now, sigma Fy equals 0 gives me plus 27 minus 3.6 into 3.6 into we have to calculate this distance because that is where the load is applied. So what is this distance? If the total distance is x and this we know is 7.5, it will be x minus 7.5 minus Vy equaling 0, or Vy comes out to be 27 minus 3.6 into x minus 7.5. Why don't we simplify this? Plus 27. So this essentially, it will be 54 minus 3.6x. So now we can see that we have got a linear variation in x with a negative slope. And this is for this range. This is for this range. So at C, at point C, x is 7.5. So Vy at point C is 54 minus 3.6 into 7.5, which is 27 kilonewton. Is it consistent with what we got earlier? We are able to see that it is consistent here. Now at B, when x is 15 meters, Vy at B, it will come out to be 0. Because when we plug in x as 15, 3.6 into 15 is 54. So we have got the shear force variation. Fine. Let us let us go ahead and solve for the moments also. M about the right end equaling 0. What will that be? it'll give me, I'll do it quickly. If you give me plus MA minus 27x plus 3.6 into x minus 7.5 the whole squared by 2 plus mx equaling 0. So essentially, when I multiply this with this distance, it will give me a force like that. Moment of that force will be force into that distance, which is nothing but x minus 7.5, half of that. Both get multiplied, that is why it's a square. I suppose that most of you already know this, so I won't delve much into that. Mx, I'll get one equation, a big equation in some form. So let me not solve for it. Let us solve it by inference then. So in such a case, for this beam, I have got these 3 points and my variation with x. At x equal to 0, I calculated my shear force as, at x equal to 0, it was 27. At x equal to 7.5 also, it is 27 because it has no variation in x. So it is positive. So I have positive 27 going till that point. And I saw that at the free end, I got 0. So I just need to connect it like that. So this is positive with this is 27 kilonewton. And we said no shear force diagram is complete without the sign convention. So I'll just put the sign convention here. So this is my shear force diagram. So let us look at the options. Which of the following? So I can see that this is matching. The option B has a slope here, which implies that in the portion AC, the shear force had a dependence on x, negative dependence on x, which is not the case where it was constant. And this is not, these two are not possible because of our sign convention telling that this beam is experiencing positive shear force. Okay, so far so good. So let us look at the bending moment diagram now. Now for this section, for the section AC, I already have the bending moment values. At at A, the bending moment is negative, and it goes to another negative value at C, keeping note that it is a linear variation. So essentially what I'm looking at is I have some negative, if this be the datum 0, I have some negative value which is 303, and from that negative value it goes to a lesser negative value essentially with a linear variation. So in between x equal to 0 and x equal to 7.5, it has to have a linear variation like this. So let us look at the options. Which of the options has that option? Has that? I know that this cannot be the answer because it is positive, while our bending moment by bending moment value came out to be negative. So that essentially rules out A and B. Now, if we look at C and D, it is subtle, but the difference is that this is a line, while this is given as a curve. So that is what that we need to take care of. So this is a line, and we saw that our bending moment had a linear variation here. So this is our bending moment diagram. So let us check it once with whatever idea we have. In portion CB, since we did not solve for that big equation, since we didn't solve for this big equation, let us just verify whatever we have been doing is consistent or not. Now I know that at B, at point B, my shear force is 0. What does that imply? The slope or the bending moment diagram is 0 at that point. Now as my x increases in this direction, my shear force slope keeps on reducing from a positive value to 0. At x equal to 7.5, I have some positive shear force. That goes to 0 as I proceed in the x direction. What it implies is the slope of the bending moment diagram at C is some finite value, finite positive value, and its slope decreases to 0. Can we see if that is the case? If this be our bending moment diagram, if I draw a tangent here, I can see that this has a positive slope. I can see this is my tangent here, which has a positive slope. And at B, the tangent has a slope of 0. So from some positive slope to 0, it went. So it follows our conventions properly. There is no problem. Is it clear what we have discussed here? Are there any questions? Or if I'm covering something too, yeah, yes, please go ahead. E- Shear force, yes. Same to find out what? Exactly, exactly. I just applied it to one portion because the equation was too long. You're absolutely right. The thing is dm by dx is equal to v. We have this recipe for our given sign convention. And it so happens that the sign convention with which we derived this is the same that is being applied to this problem. So if we don't draw all this, once we have successfully drawn the shear force diagram, we can see that, as you had mentioned, that in portion AC, I have a finite positive slope. And from C to B, my finite positive slope decreases. So which of the quantities, which of the options here has a finite positive slope in portion AC? Option C has and option D has. Only thing is option C has a varying positive finite slope, while option D has a constant positive slope. So what you said is absolutely right. Only I had applied it only to AC, only to CB portion. You could apply it to AC as well, for the whole beam as well. I think my screen is not getting presented, or 1 minute. I'll just, yeah, you please go ahead and ask. Yes, exactly. So that is why this question says qualitative. If it is quantitative, then naturally we cannot use this equation. Instead, we would have to go with the actual equation. Am I answering your question correctly, or you were asking something else? Okay, okay. That is what you're asking is, if let us say at x equal to some 8 meters, what is the bending moment they have asked? In that case, this will no longer serve our purpose, because this is only qualitatively telling us how the slopes at key points will vary, based on which we have to develop the diagram. Okay. So with that background of understanding, let us try to address this problem, but we'll do it a little quickly, because I understand for people who are familiar with it, the circuitous route I'm taking might be a little overkill. So let us try to solve this question a little more quickly than we have done for the past ones. So let me consider the beam. I have AY and I have BY. I will not label AX because AX is anyway 0. So this is 3 kilonewton. And from this point, I have a varying load like that. And at this end, the load is 9 kilonewton per meter. So this is point C, this point D, A, B. Total length is 8 meters. This distance is 3 meters and this is 4, which makes this distance 1 meter. Okay. Yeah, okay, I've already added the page. So this is my problem. So if I take moment about B, I can get, okay, first let us see what is the thing that is asked in the question. Consider a simply supported beam with loading as shown as per the sign convention given. Okay, what is the magnitude of the vertical reaction at AB? What is the value of shear force as you had just asked? At point D, what is the shear force, or what they are asking? How the qualitatively, how bending moment diagram and shear force diagram, that goes to another question. So this question ends here. So let us calculate the reactions quickly. I'll take moment about B to be 0, which gives me minus AY into 8 plus 3 into 7 plus half into 4 into 9 into 1 by 3 to 4. So when I have a triangle like that, I'll have its resultant at this point, 1/3 of the base. So that is what has been applied here. I suppose it is clear. So, okay. So I'm getting 5.625. If you guys are also solving along, you please verify that it is correct. So I have got AY to be 5.625 and summation of forces about the vertical equaling 0 will give me By equal to 3 minus, sorry, minus 3 minus 3 plus half 9 into 4 minus AY. Gives me 15.375. Naturally, because it is loaded more near B, so its reaction also will shoot up appropriately. Okay, so we have answered these two. I have the vertical reaction at A and then vertical reaction at B is answered. So the value of the shear force at point D in kilonewton as per the given sign convention is what is asked. Now, there is one benefit of having this sign convention in the sense that if I invariably take my positive to be pointing like that, which will be so in most of the cases unless there's a special condition. So if I have my V pointing like that, whenever I draw the free body diagram with X point increasing in the right direction, if I draw the free body diagram with X increasing in the right direction, invariably I'll have to put my shear force like that. Shear force will always be pointing downwards when I take a section like that. In which case, whatever be the applied load, sigma Fy equaling 0 will always this quantity will always have minus Vy, in which case I need not consider that. If I add up the rest of the forces as per the sign convention, that is the shear force at that section. I don't know if I've conveyed the point properly. What I meant to say is, if let us say there is some force here F1 and a force here F2. If I have it like this, so when I apply sigma Fy equal to 0, it gives me F2 minus F1 minus Vy equaling 0. Or if I take Vy to the right side, it gives me F2 minus F1 equal to Vy. So this implies that I need not cut a section, put the shear force there according to this sign convention, and then solve for it. What this is essentially telling me is that I just need to add up the forces, and that straight away gives me the shear force at any section when I use this sign convention. So that is beneficial for me. In such a case, can I quickly draw the shear force for this beam, shear force diagram for this beam? Let me just copy this. I'll just put it here. So at A I have AY that is acting. AY is some positive quantity, some 5.75 something we saw. And then it is constant till C. And I just need to add. So if this is 5 point, how much was that? 5.625. Then this will be 5.625 minus 3. And I keep going till D. Till point D, I keep going. And then as I take section from D, as I keep on taking section, I just need to account for that much of area and subtract it out of my equations. With the understanding that at D, the triangle is 0, which means at D I will have a unique value. There won't be any jump. So at B, can I calculate? At B, it will be 5.625 minus 3 minus the area of the triangle. We will notice that it is nothing but by. So by came to 15.375. So it will go from here to 15.375 here. So this will be negative. This is positive. So this is the shear force diagram for that beam. 5.625. Yeah. Yeah. Good point. Yes. Let me come to that. Yeah. What you said is right. Good catch. In fact, let me delete this. It'll have some variation. Okay. Have some variation like that, and we'll see from the equation why that is. So if up to this point, the left side, it is clear. Now if I take a section at a distance like that, at x, so my force will be Ay. Yeah, the thing is, I put By here and then connected it by the line. What I should have done is, I can take this relation dV by dx is minus W. And mind you, this equation, we have derived it for a W which was facing downward, which is similar to our case here. So W goes like that. So far, so good. But W is a function of X. In the case of UDL, W is a linear function of X. W is a constant function, essentially. It doesn't vary with X. Whereas in the case of a triangle, W is a linear function of X. W is essentially equal to 9 by 4. This is our W. Because we can see that it's a linear function. So what that implies is, if this is a linear function, yeah. So if this is a linear function, then our area, essentially at this point, whatever the force that is applied, how will we calculate that? Let me draw that in red. At this point, my force that is applied, W that is applied, is half into, let me call this distance as x into 9 by 4 x. So there comes my quadratic variation. I think I convoluted this a little bit. You please let me know if this is not clear. I'll clarify it threadbare. I hope that this is clear. In fact, why don't I take a section at that point and solve it? I have a force that is applied like that. And then from here, I have a uniformly varying load applied like that. If I take x to be this is 1 meter, this is 3 meters, and this is some point which is, I have a force like this, which is Ay. This is 3 kilonewton. So what will this be? This will be 9 by 4 into D, with the understanding that this is D. So D and X we can relate. Now if this is the free body diagram, in that case Vy will be like this. Vy will be like this and Mx will be like that. Okay, so adding up Fy equaling 0 gives me Ay minus 3 minus half into d into 9 by 4 d minus Vy equaling 0, or Vy equal to Ay minus 3 minus 9 by 8 t squared. This is the relation I have got in terms of d. Now I just have to relate it to uh, x. So I can see that x minus d from this from x and d, I can see that x minus d is nothing but 4, or d is nothing but x minus 4. So if I substitute that here, I'll be able to see that it is ay minus 3 minus 9 by 8 into x minus 4 the whole square. This is essentially my shear force equation. And what is the domain of this? This is from x equal to 4 to 8. From 4 to, I think the total length was 8. Yeah, 8. So I hope this is clear. So we can see that it has a negative slope and a quadratic dependence. So which is why it goes like that. Is it clear? Now I think I did some justice to explaining it, because earlier I think I convoluted it a little bit. Is it clear? Or if there are any questions, please go ahead and ask. I'll try to clarify that. I hope this is clear. Could I just get a confirmation on this, please? Clear. Okay. Okay. I hope. Okay. Okay. All right. In such a case, let us look at the options here. Now, this has a linear variation. We can clearly see when would this be if we had a beam. If we had the same beam, which was like that, and a load applied like that, and then we had a UDL. If a UDL were applied, then this case would hold because it has a linear variation. Right now it is having a quadratic variation. So essentially, this is correct. Now we can check for the slopes here. Now if I see the slope at this point, I have a negative slope which gets more and more negative as I go in x, right? Which is consistent with this. So which is why this slope is actually correct. I hope this is clear. So as we go about, we are able to see that our slope here was a negative quantity which became more and more negative. Okay, so I hope that this is clear. Which is why this is the shear force variation for that, and not these. Because I'm able to see here that slope increases slowly and comes to 0 from a negative quantity, which is not consistent with our equations. Which is why these two options are not correct. Okay, so let me move on to this question then. Yeah, so consider the simply supported beam with loading as shown as per the sign convention again. So what we saw is when we have a sign convention like this, if I take a section from the left with x varying in the positive right direction, in such a case, to arrive at the shear force at any section, I just need to add up the forces, keeping in mind that I don't mess up the variation in between those key points. I account for the variation in the load, which is what happened in the previous question. So with that background, what is the magnitude of the vertical reaction force? So essentially it will be minus Ay into 8 plus 2 into this 6 plus 12 plus 4 fours are 16 plus 12 minus 4 equaling 0. So AY I can calculate from here. So this comes to 4.5 kilonewton. Anyway, rest is a clerical exercise. I don't want to, get into that. Instead, we can directly solve for these questions. What is the maximum shear force that is experienced by this beam? Now I can see if AY is 4.5, I can see this goes to 4.5. Then it will get reduced by 2. Then it will further get reduced by 4. Then it will get reduced by 6 and close here. So I am able to see that the maximum reaction, that is the maximum shear force, would naturally occur at this end. And can I calculate that? It will be AY minus the sum of all these forces, which is 12. AY minus 12, so it is 4.5 minus 12, which is nothing but 7.5. So it is 7.5 kilonewton here. Similarly, bending moment, if I see, what is the bending moment at D? Now, as we discussed for the shear force, let me also just briefly explain for the bending moment also. Let us say that I have a section like that with some force applied here, some force applied here, and a reaction here, 2, 4. And I have moment applied like that. Now, when I do sigma mx equaling 0, essentially I'll be getting, if this I have it as x, I'll get minus ayx plus 2 into, say this is into 2 plus 4 into x minus 4 plus mx equaling 0. So essentially whatever, if I add up, I'll be getting the negative of the bending moment here. So I hope that that is clear what I'm trying to say. So I can quickly write my equation this way. I just have to substitute for x. Now if I substitute x equal to 4, 4, essentially I should have taken a section here somewhere, with the understanding that bending moment is continuous at this point. Why bending moment is continuous? Because I don't have any couples applied. If I have a shear force applied, it only creates a jump in the shear force diagram, not the bending moment diagram. If the bending moment diagram is continuous, it doesn't matter which section I take. So if I have taken a section here and I substitute x equal to 4, I should still be able to get what the bending moment is. So with this equation, if I substitute x equal to 4, I'll be able to see that this contribution already gets nullified and I can get my bending moment easily. So let us go ahead and do that. It is 4.5 into 4 minus 2 into 2, which is 9. 18 minus 4, which is 14 kilonewton meter. Mx, essentially this is not x, since I have substituted x equal to 4, this is md. So this is my bending moment at point D. So the bending moment variation, again we can apply this logic, the equations, that bending moment slope will be constant, but it will have different slopes, with the understanding that it is positive. So in such a case, how will the bending moment diagram look? I go from here, I have one slope till here, then again I have a positive slope, but it is of lesser magnitude, then it has a negative slope, Then here, since there is a couple applied, I'll have a jump, and then it'll go like that. Something similar to that, the bending moment diagram will come. We can see that if we are able to calculate these quantities at the key points, we can easily plot the bending moment diagram at once. So, so this we have answered. So I hope that that is clear. Are there any questions? Minimum or maximum, it is just a question of our sign convention, right? If I were to, let us say, if I were to take a convention where I put this in this direction, in such a case, wherever my bending moment diagram just gets flipped about the x-axis. So whatever was maximum will now be called minimum. I suppose I've done some justice to explaining how shear force and bending moment diagrams are drawn, and how to go about considering sign convention, why we need sign convention, and how do we employ them in problems. And we saw problems which have a variation of load between a concentrated load, a uniformly distributed load, and also a uniformly varying load. Now, given this background, I suppose you will be able to solve any problem pertaining to beams, even with a non-uniform slope. Non-uniform variation, essentially it is just the area under the curve. Since it happens to be rectangle or triangle, I just simply took the area. If it is a more complex distribution, we need to go for integration. But those are actually coined problems. Those might not exist in real life, but the idea is to grasp the essence of how to draw shear force and bending moment diagram, because this will be extensively used in analysis in the next level course, which is strength of materials. So to that end, I hope I've done some justice here. So, okay, then in that case, I'll call it today. Thank you guys for attending. I'll see you next week. Thank you. Thank you. Thank you.